actually been into the office a couple of times. No, not very often, I must say.
You're not in the office right now?
No, we're all in home office now.
CERN is closed?
Effectively, I mean, it's people who absolutely cannot work from home are allowed to go in, which is essentially the experimentalists. Well, not even all of them, right? The people who actually have to construct the LHC in the tunnel, they are allowed in. But everybody else is very, very strongly encouraged to not come.
Okay.
Okay, so maybe we can start now. So this is the second inflation lecture by Valerie. Please go ahead.
Okay, thank you. So let me start by very briefly recapping where we left off yesterday. And so what we talked about yesterday was the horizon and the flatness problems, which in particular led us to conclude that in kind of standard cosmology, so we have matter domination and radiation domination, we kind of have this problem of the increasing co-moving Hubble horizon, and this kind of occurs in particular always when this equation of state parameter omega is bigger than -1/3, right? And we saw that we got very severe fine-tuning problems. And we already understood yesterday that in principle, all these problems go away if we assume that we had some phase in the very early universe where this equation of state parameter is smaller than -1/3. And then at that point we stopped, right? And we were already puzzled about what is this strange equation of state, right? Negative pressure, what does this mean? And so this is essentially what we're going to start today. So we want to essentially construct a model where this weird equation of state actually happens. So a bit bigger. Okay, so we start with essentially the simplest model of what we will call slow roll inflation. And we will consider very simple model, very simple quantum field theory with only a single real scalar field phi. So the action in this case is just given by, here we have the determinant of the metric, and then we have the Einstein-Hilbert term, which is just a Ricci scalar. Recall that I'm setting the Planck mass to 1. And then we have a kinetic term for the scalar. And we have a potential term for the scalar. Okay, so the first term here is this here is essentially the Einstein-Hilbert part of the action, and this is really what is associated to this real scalar field. And now, if we want to kind of understand the dynamics, understand the equations of motion, understand kind of what's going on with Einstein's equation, what we need is the energy momentum tensor. And in particular, I want to look at the energy momentum tensor, the contribution from phi. So we can get that by doing a variation of S with respect to the metric. So a prefactor, which is essentially convention. And then we do a variation of the metric with respect, the variation of the action with respect to the metric. So essentially if we do the variation here on this power of the metric here, we will just get 1 times the square root of g, which cancels with this guy. And then we are left with del mu phi, del nu phi. And then we also have to, however, do the variation with respect to this factor g in front, right? Because this contains the determinant of the metric. And here you have to be a bit careful with your minus signs and with geometric convention. But what you should get is minus g mu nu, where this comes from the variation of this prefactor. And then we get 1/2 del, let's say sigma phi del sigma phi, plus the scalar potential. And now recall that if we want to think about an ideal gas, we want to describe this as an ideal gas, we know that this is supposed to be some diagonal matrix where the first component is the energy density and the spatial components are just the pressure. So from this equation, I can now directly read off what the energy momentum and the pressure are supposed to be. And to do so, I will kind of simplify my life a bit, and I will assume that this scalar field phi is homogeneous. So I'm going to assume that phi, which is in general a function of position and time, is only going to be a function of time, right? So this means it's homogeneous, or in other words, what it means is that all the spatial derivatives are zero. And then this kind of becomes a fairly simple exercise. So if I want to find what is rho, I need to take the 0, 0 component of T mu nu, right? So I get a phi dot term from here. I will get a minus 1/2 phi dot term from here, and I will get the scalar potential from down here. So in total, I will get 1/2 phi dot squared plus V of phi. And if I want to know, and let me give this an index phi, right, to remember that this came from the phi part of the energy momentum tensor, can do the same for the pressure. And again, we have to set, now we have to take the spatial part, right? So we set the mu and nu to say I and I. So we will, but then we also have to remember that we have this condition here, right? The homogeneous field. So we will not get any contribution from the term in front. We will get a contribution from inside here. So we will again get the 1/2 phi dot square contribution. And we will also again get the scalar potential now with the opposite sign, because we're picking up the opposite component of the metric tensor, right? I mean, this has a minus plus 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 signature. So before we picked up the minus, now we pick up the plus. So in total, we get the opposite sign, minus V of phi. So these are simple enough expressions, this guy and this guy. So we can now compute the equation of state parameter, which was just P divided by rho. And this is just 1/2 phi dot squared plus, minus, the only important sign that matters here, minus V of phi, 1/2 phi dot squared plus V of phi. And in particular, if we now go to the limit, if we take the limit that the kinetic energy is much, much smaller than the potential energy, in that case, this just goes to -1. And -1 is in particular smaller than -1/3, right? So we are done. We have essentially found a system which is just a single scalar field, which is homogeneous and whose kinetic energy is small compared to its potential energy. And this system, if we compute the energy momentum tensor, results in an ideal fluid, which has an equation of state parameter, which is very close to -1. So this is essentially already has all the ingredients that we needed to solve the problems that we talked about yesterday. I see a comment in the chat that is it now fine? Can you see full screen? I assume yes, unless somebody shouts. Okay, perfect. And now, once we have this, right, so we have the equation of state parameter. So if we want to understand the dynamics of the system, we need the equation of motion. And to get the equation of motion, what you need to do is you need to perform a variation of the action with respect to the field. And insist that this is 0. And this is, in fact, an exercise that I'll ask you to do on the exercise sheets. So we have the action up here, right? So to get the energy momentum tensor, we did a variation with respect to the metric. So now essentially you play the same story, but you do a variation with respect to the scalar field, right? to phi and to also phi mu, the Euler-Lagrange mechanism, well, Euler-Lagrange system. And then what you will get is this expression here, del nu square root of minus g del nu phi plus v prime of phi is 0. And if we now again assume as before, we take phi to be homogeneous, and we are only going to use the FRW metric, then under these assumptions, you can again drop all the spatial derivatives, and what you will get is simply an equation of motion where you have the second time derivative of phi, then you have the Hubble expansion because we're in an expanding universe, and finally you have this term over here, right, which is v dot phi equals 0. So this is referred to often as the well, it's the equation of motion for the scalar field. It's often called the slow roll equation of motion. So this gives you the time dynamics of this field phi, assuming that you know the time dynamics of the Hubble parameter. And the time dynamics of the Hubble parameter is given by the Friedmann equation, right? So this can be, to good approximation, just written as, like if you remember, there was a rho and a p here, right? So we can use the rho and p from above. Well, actually just rho, phi dot squared plus v of phi. And I've dropped the term, this term here, the k over a squared term here. And I'm going to assume that this is much smaller than rho. And the reason for this, so the logic may seem a bit circular, but like if you remember the flatness problem yesterday, we saw that if we have an equation of state parameter which is smaller than minus 1/3, then essentially the flatness problem is solved in the sense that the universe, as it expands, becomes flatter and flatter, and this term becomes less and less important, right? So here now I'm essentially saying, okay, I already know that in the end I will be able to drop this term, so I won't complicate my life too much by dragging it along the whole time. So I will kind of, for convenience, make this assumption here. And then if we want to actually compute the dynamics of the system, really we only need these two equations, the equation of motion for phi and the equation of motion for the scale factor. So these are fairly important equations for the following. Okay, I see some questions.
Valerie.
Yes.
Valerie, I have a small question. This equation of motion, it is supposed that the field is not interacting.
Right.
It is not self-interacting or interact with the other components.
It can be self-interacting, right? The v of phi here is general. So this could be some phi squared or phi cubed or phi to the 4 potential. So it can self-interact, yes, but we have not included any other particles. We're just having just this field phi and gravity and nothing else.
Okay, okay, thank you. Because in principle, we may have some interaction, and this change, for instance, the slow hole phase, and the conditions for the slow hole phase. If the field interacts.
Yeah, but we're not quite there yet, right? I mean, now we just have the equation of motion. This equation of motion made no assumptions about v of phi.
Okay.
So this I think should be there's no assumptions here on v of phi. Then there was a question in the chat, correctly kind of wondering about kind of why kind of, I mean, it's maybe kind of intuitive that the kinetic energy contributes to the pressure, right? But what does it mean that we have a negative contribution from this potential energy, right? And yeah, I mean, what this negative pressure essentially means is that this vacuum energy, right, this v of phi, is really kind of expanding your volume, right? So, I mean, normally kind of pressure is something that, you know, pushes a volume together. But here, this minus v of phi is really kind of an expanding force. And this is, at the end of the day, what this is telling you is that the vacuum energy, or this v of phi, this energy in the scalar potential, is essentially a force which is really driving the expansion of the universe. And this is counterintuitive, right? But in some sense, we here just, and I fully agree that's counterintuitive, right? But essentially, this is why here we kind of really just kind of compute it in a very simple system. And sometimes we just trust our equations at the end. Concerning the interpretation of the phi field, well, at the moment, this is really just kind of one single field that I introduced by hand, right? I mean, then later on, one can wonder, does this maybe have something to do with the standard model Higgs field, or maybe some field in a supersymmetric theory? But at the moment, I'm just kind of, this is just a toy model, right? And I'm just kind of introducing a single field by hand. At the moment, there's not even any standard model here anywhere, right? I mean, it's really just a single field. Okay. So let me continue. So now we have these equations of motion, and now we can compute the dynamics. So using, so if you recall the first Friedmann equation, oops. Which just said that the Hubble parameter, right, is A dot over A. Is 1/3 of the energy density, then you can now, given what we said above, right, you can essentially solve this immediately, and you will get, well, I mean, in fact, this is something which we did in the yesterday, right? We from this what we derived yesterday is that rho scales is a to the -3 1 plus omega, and now what we're interested now is the limit omega equals -1. And in this limit, we already hinted at this yesterday, right? Then this exponent is just 0, and we find that the energy density is constant. And this is pretty weird, right? Because energy density constant, if the volume is changing, means really a change to the total amount of energy in some co-moving volume. So in particular, in the same limit, so again for omega equal -1. You can directly from this equation here, right? You have A dot over A is some constant. So then, of course, you know what is the solution to this equation, right? It means that A has to be some exponential function. And the argument of the exponential function is just what is here on the right-hand side. So we know that the scale factor is just proportional to an exponential function of h times t. So we get exponentially expanding space with constant energy density inside. We can also, in this limit now, compute exactly what is tau, right? So tau was a co-moving time, right, and or conformal time, and it was defined as dt is ad tau, and so we can rewrite this as -1 over ah, and this will be something that we're using in the following. And I mean, there's a bit of a, there's a bit of a question, kind of where you put the 0 point here, and there's different conventions. So what I'll be using throughout all the time when I'm discussing inflation, I'll be using the convention that tau is defined in this way. And during inflation, essentially tau runs from -infinity to 0, right? So maybe it's a bit strange that I would choose the negative axis to define time like this, but it turns out to be the more convenient choice here. So in summary, to finish up kind of this dynamics part, we get an exponentially expanding universe. Oops. Dominated by the potential energy of a scalar field. Okay, any questions so far?
Sorry, can I ask, is related to what I asked yesterday. So again, if we have an equation of state with -1, so this is exactly what dark energy, right? It's a constant, like a cosmological constant, right? So the density then, so the density of the other components of the energy density will decay more rapidly than this component, right? So even if it's a very small amount of this fluid, whatever this inflaton, I guess, is the scalar field, right? So it's supposed to, unless it changes with time, right, which is what you already assume, I guess. You say it's a function of time, but if it's just a constant, then eventually it will dominate again, as the universe evolves, right? Because the other components of the energy density decay more rapidly, right, with the expansion.
Right. So here, what we in fact, exactly, so what we need during this early epoch of inflation, what we need is this component to dominate, right? And then, as you say, because it grows faster than anything else that we know, if we really kind of assume we need a way to end this, right? This is essentially what you're saying, because let's take the limit where omega is exactly -1, right? So we have some exactly flat potential and we just kind of have some kinetic energy and we're just moving along. Then you would never get out of this phase, right?
Correct.
Because there's no way any other component could overtake this. So yes, we'll need a way to end this, and essentially the way to end this is that, I'm trying to sketch it here, right? So this V of phi, right? You can imagine it being maybe something, for example, like this, right? Where kind of here you are rolling slowly, right? We have small kinetic energy, and then at some point you reach some point in your scalar potential where the potential becomes more steep, right? And the kinetic energy overtakes the potential energy. And then you can exit this phase.
All right, okay. Thank you, yeah, very good, thank you.
Okay, any more questions? Okay, but I think, I see some questions in the chat, but scrolling over them, I think you have largely answered them to each other. So I think everything is clear, but let me know if there's still something open. So for doing computations, because like now we kind of understand the rough picture. Now for doing actual computations, it would be useful to use the so-called slow roll approximation. So why is now? So I have a backup plan if this fails, but let's hope it sticks with me for a bit more. Okay, slow roll approximation. And the reason essentially I want to go into this is because, I mean, at the end of the day, we want to compute actual observables, right? So essentially I want to give you a concrete scalar potential, right? Whatever m squared phi squared. And I want you to essentially be able to compute, okay, kind of this is the amount of expansion that we had, this is the evolution of the scale factor, this is the evolution of the scalar field. And then later, as we continue, also kind of, okay, this is the evolution of the quantum perturbations, and then this will be the predictions, for example, for the cosmic microwave background. So in order to do that, we need to go from a qualitative picture to really a quantitative picture. So we have already introduced this parameter epsilon as minus h dot over h squared. This is the so-called first slower parameter. And we can rewrite this using, again, the Friedmann equations as 1/2 phi dot squared over h squared. I'm setting again the Planck mass to 1. And we also saw yesterday that essentially the condition to have inflation, so the condition to have accelerated expansion, implies to having this slow roll parameter smaller than 1. Yeah, so this is essentially really the definition of essentially having inflation or having accelerated expansion. And there's also a second slow roll parameter, which is often referred to as eta, which we will now define as the second time derivative of the scalar field. So h phi dot. And we will also require this guy to be smaller 1. And this is essentially saying, okay, as long as this guy is smaller 1, as long as eta is smaller 1 in some sense, because this is more or less the time derivative of this guy, this means that this epsilon parameter is changing slowly, which means if it starts off to be smaller 1, it will kind of stay smaller 1 for a longer period of time, right? So essentially, this is what we need in order to get sustained inflation. So inflation over a longer period of time. And these two guys, epsilon and eta, are referred to as the slow roll parameters. And in the the slow roll approximation, we will assume essentially these not to be just smaller than 1, but really much smaller than 1. Now, for practical purposes, it is more convenient actually to introduce what is called the potential slow roll parameters. Which are defined not with respect to phi and phi dot, but which are defined essentially by directly taking derivatives of the potential. So in particular, epsilon is then, and now here I introduce the Planck mass, just kind of so you see how the dimensions play out, is v dot phi over v squared, and eta v is m Planck squared, second derivative of v with respect to v. And if we are in this slow roll limit, so if eta and epsilon are much smaller than 1, then essentially this epsilon v is more or less the same as the epsilon above, and the eta is the eta v minus epsilon v. So if you know one set of parameters, more or less you also know the other. And the reason the second set is more convenient is that if I give you a model, right, I tell you, okay, this is m squared phi squared scalar potential, you can immediately compute these parameters. Whereas if you want to compute the parameters up here, you first need to solve the equation of motion and need to understand kind of what is the time dependence of phi. So the second set is a bit more practical to work with. So now we can go back to our equation of motion of before, right? And look, see what like this blue box up here. And we can ask kind of what do these equations look like in this slow roll approximation. So,
excuse me?
Yes?
For the eta, you didn't forget the epsilon? It's not minus epsilon after the term of the potential?
No, but...
okay, you didn't
here.
define it. Okay. Yeah. Okay.
Yeah.
Okay, thank you.
Yeah, thank you. Right, so in the slow roll approximation, the equations of motion, then we can, because essentially, if we take eta and epsilon to be very small, we can in particular ignore the phi double dot term. And then we just get, as a slow roll equation of motion, 3h phi dot plus v prime phi is 0. So it's just a first order differential equation, which means there's only one single initial condition, right, which is kind of where you start rolling. But at every point on your potential here, essentially the velocity at which you roll is a simple function of where you are, right? There's no initial velocity as an initial condition. And the Hubble parameter, which is given by the energy density, in the limit that the kinetic energy is much smaller than the potential energy, is simply given by 1/3 times the potential energy, which is constant, right? This is precisely the omega goes to -1 limit, and hence the scale factor is proportional to e to the ht. So these are, if you want to compute anything, these are essentially your starting equations. And now I can also answer a question that came up yesterday, which was a question of like how many e-folds of inflation do we have? So what these e-folds is essentially a time coordinate which is used in the literature for this. So we're going to introduce a new time coordinate. Oops. Which we call e-folds. So this is essentially, we've already seen we can use essentially time as we have physical time, we have conformal time, we also have the scale factor as a time coordinate. So here we introduce another, and it is defined essentially as dn, where n counts the number of e-folds, is minus h dt. So what this means is essentially the number of e-folds counts the number of Hubble times that have elapsed in a certain time period. So we can, if we integrate this, then we get n is essentially the, if you recall that h was a dot over a, right? So we get the number of e-folds at some point in time during inflation is the logarithm of the scale factor at the end of inflation divided by the scale factor at some point in time that I'm interested in, where this index end, right, the end of inflation, is precisely when epsilon equals 1. And this, then, according to this equation, is minus h dt. And I'm going to absorb the minus by flipping around the initial and the final coordinates of the time. Then we can rewrite this in a function of phi instead of t, because phi is again moving as a monotonous function of t. And then here you already recognize this is the first lower parameter, or the square root of the first lower parameter. So I'm going to flip again the integration boundaries to absorb the minus sign. And then we have 2 epsilon, well, let me just call it epsilon, not specify which epsilon. Approximately they are the same, d phi. So, and this essentially specifies is a time measure for the amount of inflation between the end of inflation to some point phi, which marks some point in time during inflation. And in order to solve the horizon and flatness problems, right, you essentially need a certain amount of expansion of the universe. And this certain amount that you need, it depends a bit on the details, but approximately you need something like 50 to 60 e-folds of inflation. So from the horizon and flatness problem, you would conclude that n should be bigger than about 50 to 60 or so. You can only put a lower bound, right? Because you can also, I mean, you cannot kind of, there could have been, because we essentially only have, yeah, there could have been an arbitrary amount of inflation at extremely early times, right, which we cannot even observe. But essentially, what we need to explain the observed homogeneity and flatness of our universe is this order of magnitude. Okay. So yeah, one question in the chat was why are epsilon and epsilon v the same? So you can essentially see this like they're only the same under this assumption, right? So you can essentially using the Scalar equation of motion, you can kind of see that these are kind of similar under this approximation. I mean, essentially you can see it if you look at, where's our equation of motion gone to? Here, right? This guy equal to this guy is the equivalence of the 2 slower parameters. So as long as you can drop phi double dot, the 2 are the same. So the question from Disha, like, where does this number 50 to 60 come from? Well, recall, okay, I don't have the plot here, but okay, so for example, for the horizon, if you recall the horizon problem, right? It's maybe the more simplest to explain. We had this picture here, right? That we had the observer, we had the path light cone, we had some time of the CMB decoupling, right? And we had some time where we thought essentially that we had t equals 0, and we essentially wanted all of these light cones to overlap, right? So we essentially need to extend back in time here until this light cone way over here and this light cone way over here overlapped in time, right? And so this defines a certain time period, and this time period is 50 to 60, roughly, right? It depends on the details of the model, but essentially, in order for the light, if you observe the CMB in one direction and you observe the CMB in the other direction, and you want that these two photons arriving at you from two opposite directions had time in their cosmic history to interact with each other so that their two past light cones interact, that gives you a bound on how much inflation you need. And this is roughly the number. And I cannot give you a precise number because it depends essentially on the details of the inflation model. It depends in particular on what is the energy scale to which the universe reheats after the end of inflation. Yeah, exactly. I mean, all points that we see in the CMB are kind of causally connected if we use this number. But of course, we do not know if maybe even more points could also have been causally connected, right? So this is why it's only a bound. Okay, so let us do a minimal example just to show you how this works. So let's just take the scalar potential of, just let's say we have a massive field, right? V is 1/2 m squared phi squared, m is the mass. And now we can compute with the formulas above, right? We can compute epsilon. So we need to take the derivative, right? So then that gives us m squared phi. Then we need to divide by v and take the whole thing squared. And then if we include the Planck mass, we get 2m Planck over phi squared. To have inflation, we require this to be smaller than 1. So from this, we can already compute the end of inflation. Just solve this equation, right? You get the square root of 2 times m Planck. So this was epsilon equal 1. And we essentially have inflation as long as this condition holds. So we have inflation as long as phi is larger than phi end. Now we can compute, again, using the formula above, we can compute the amount of ethols, right? So 1 over m Planck, phi end over phi 1 over 2 epsilon d phi. You plug in the expression for epsilon here. You perform the simple integral. You get phi squared divided by 4 m Planck squared minus 1/2 equals 60. You can essentially forget about the 1/2 because 1/2 is not much compared to 60. And so the starting point of inflation, or the latest starting point of inflation, is about 15 m Planck. Okay, so if we draw a picture, v of phi, function of phi, it's just the m squared phi squared model. There will be some starting point here, right, where this is, do this in units of m Planck. So here we have 15, here we have square root of 2. And essentially, as long as you are rolling here, you will have inflation. So all of this is inflation. Where maybe it starts earlier, but it has to start here at the latest. And then here is the endpoint of inflation. And this period between these two lines corresponds in our calculation now to 60 ethols. And then down here, the potential energy becomes small, right? Potential energy goes to 0. And hence the equation of state parameter is no longer smaller than minus 1/3, simply because the potential energy goes to 0. So in this period here, you have omega smaller than minus 1/3. So this is essentially the mechanism. So I think it's pretty remarkable. At the end of the last lecture, we were kind of wondering what sort of a bizarre model do we need to get this omega smaller than minus 1/3? What sort of weird thing is this? And now what we find is that a simple case of a massive scalar field essentially accomplishes all that we need at this level. Okay, are there any more questions? And one of the exercises that I will put online later today is that you essentially repeat a similar procedure for a slightly more complicated scalar potential. And essentially different in a very simplified way, different inflation model building essentially, okay, I have to be careful what I say. In an overly simplified way, inflation model building consists of writing down different scalar potentials and computing the dynamics of the scalar fields and these potentials. And then, of course, you have to match it to the observables. Yes, correct. Answering to Disha's question in the chat, yes, we're still, from the start, we assumed that it's a homogeneous field, and we're still assuming this now. Yes. Okay. So now I'm going to change gears a bit, and I'm going to talk about cosmological perturbation theory. So, because so far we talked about homogeneous field the whole time, right? But in the next lecture, we'll have to talk about perturbations, because we don't, as I kind of mentioned in the beginning, we don't only want to explain the expansion of the universe, right? This in some sense we have now accomplished. We've solved the horizon Inflaton's problem. But at the end of the day, we want to kind of explain the teeny little inhomogeneities, which will explain the inhomogeneities in the CMB and which will explain the seeds for galaxy formation. And so for this, it's not enough to just deal with an exactly homogeneous field, but we will deal with an approximately homogeneous field, which has some small fluctuations. And this is kind of a topic. I'm going to do it in a slightly abstract way in a second. So you will even wonder what on earth does this even have to do with inflation? And I'm doing that on purpose because it's actually kind of a tool which you need not only to understand inflation, but you will actually also need to understand the other lectures of this week, because it's such kind of a general concept in cosmology. Okay, so then without further ado, let us start the last 20 minutes of today. Cosmological perturbation theory.
Valerie, please, I have a question. It's a question about the sustained inflation. We need sustained inflation because we want to solve the cosmological problems, horizon and the flatness problem. But then, with the definitions you have used, we need semifolds between 50 and 60. And then the universe needs to expand for a long time, for many folds, and then it becomes very cold. The early universe becomes very cold.
Yeah.
Right? And then we need to reheat the universe.
Yeah.
And this is a problem or not?
No, this is not a problem. No, this is not a problem because you have, okay, maybe we can discuss in more detail at the end of the lecture or the question and answer session, because I'd like to get to the cosmological perturbation theory. But essentially, when inflation ends here, right, you still have a lot of potential energy, really a lot in units of, I mean, you can compute, right, because this phi n, right, was order 1 times m Planck, right? So the energy is still m squared m Planck squared. This is a lot of energy, right? And essentially, if you convert this energy into a thermal bath, you get a thermal bath with a very high temperature. And that is essentially what then is the initial conditions for the hot Big Bang.
But this is a very extreme process, because the universe is in a very high temperature. It goes to 0, and then it needs to come back basically to the same temperature, you know?
No, but this is automatic because we assume the homogeneous field, right? So if the field is exactly homogeneous, you will release exactly the same energy everywhere in the universe, and hence you will end up with a thermal bath of exactly the same temperature. Of course, in practice, not exact, right? This is why we need to talk about perturbations. But maybe we can discuss this in the question and answer session, okay? Because I think this goes a bit beyond what I'm currently doing.
Thank you.
Okay, so I want to consider small perturbations around a homogeneous background. So consider small perturbations around an homogeneous background, so take some quantity x, where x at the end of the day, it could be the inflaton, right? It could also be the metric, anything, which depends on t, time, and space. And I'm going to expand it at some average quantity, which only depends on time, and then some quantity, which is the perturbation, which depends on time and space. And everything that I'm going to be saying now until the end of the lecture assumes that delta x is much smaller than x bar, so that we're really looking at small perturbations, and hence it will be sufficient to do perturbation theory to linear order in delta x, right? So everything that I say will just be true at linear order. So to understand this problem, it's always good idea in physics to first think about symmetries. And the symmetries of the problem, right? We have a GR, underlying GR theory. So we have general coordinate transformations. But then this complete general symmetry of GR is actually broken by the FRW background. I mean, we hinted a bit already at this yesterday, right? That the FRW background, it kind of distinguishes between space and time, doesn't treat space and time on equal footing, right? So scale factor is a function of time, but not of space. So we have essentially some spontaneous symmetry breaking process, which is induced by this Friedmann-Robertson-Walker background. And it breaks these general coordinate transformations down to global spatial rotations, right? So it breaks it down to an SO3 group of global spatial rotations. So this essentially means if you look at the FRW metric and you kind of look at the spatial part, you can factor out the scale factor. And within the spatial part, you have all the symmetries of the rotation. But once you kind of want to include the time direction, you need to worry about the expansion of the universe. Now, since we are going to work in linear order in these perturbations, it will be convenient in a second step to do a Fourier decomposition. And the Fourier decomposition essentially singles out a single vector k, right? And so this is only something you can really do sensible if you're doing in linear order and perturbations, because otherwise you kind of get convolutions of delta k integrals. But if you're doing linear order perturbations, you can kind of do Fourier decomposition, and you can drop in all your equations, you can drop the integral on the outside, and you can just kind of work in essentially plane wave system, right? Where you have one fixed value of k, and you can do all your analysis only in that, and just keep k as a parameter. So if I single out a direction in this way, then essentially I can decompose my states into the helicity eigenstates. So essentially I take the SO2 rotations, which are orthogonal to this vector k, and if I perform these SO2 rotations, I can classify my states in terms of helicity eigenstates with respect to these SO2 rotations. So helicity eigenstates. And so some quantity x with respect to some vector k, we can perform some rotation by some angle theta in this plane, and then we will get some eigenvalue e to the I m theta times the xk. And this value m essentially now determines the nature of this state, the helicity of the state. So if m equals 0, we call this state a scalar. If m is plus or minus 1, we call this guy a vector. And if m is plus or minus 2, we call this guy a tensor. And this decomposition, so kind of starting from an inhomogeneous field, decomposing into homogeneous component plus small fluctuations, and then decomposing the fluctuations in terms of the helicity eigenstates is what is referred to as scalar vector tensor decomposition. And the reason why this is a very extremely useful tool is that at linear order in scalar vector tensor, or at linear order in these perturbations, essentially the scalar sector, the vector sector, and the tensor sector will fully decouple. So essentially, you can discuss the three sectors completely separately, and that very much kind of reduces the complexity of your problem. And the reason you can do it is precisely because essentially they are different representations under these symmetries, and they cannot mix with each other without breaking the symmetries of the problem. So to give you an example, let's do the SVT decomposition of the metric tensor. And I'm going to do this in a physicist's way and in a mathematician's way. And I think I can promise you that everybody is going to be horrified by at least one of the two options. So you can pick the one that you like best. But I'd like to give you both explanations. So the metric tensor, right? We have a 0, 0 component. We have a spatial component ij, and then we have the mixed components. And now the first step of our procedure was to introduce the FRW background, right, which separates the time component from these three spatial components. So in the physicist way of doing things, this first step just contains into drawing lines like this, right, where this is a 1x1 matrix and this down here is a 3x3 matrix. And this, as a physicist, this completes step one. Now we go to step two. Step two was kind of figuring out, doing the Fourier decomposition and figuring out kind of, do I have scalar, vector, or tensor quantities? And the way, as a physicist, the way I do this is I just kind of think about what indices do I have. So if I want to write, let's start with the simplest case, right, which is the G00. So G00 has no spatial indices, right? There's no I, no J. So in the homogeneous component is just -1. And now I would like to add a fluctuation to this, however, such that there can be no outside spatial index, right? Because I cannot kind of, introducing a spatial index would kind of introduce a vector or tensor quantity. So I can just add one fluctuation here, which I call capital phi, which is not to be confused with the Inflaton phi. And the factor 2 is pure convention, right? But this is kind of what people do. And so this is essentially all the fluctuations that go into G00 are contained in one scalar degree of freedom, which is this phi. Okay, that was easy. That was maybe a bit too easy, right? So now we have to go to the next component, to the Ji0, or because it's symmetric, right? It's also 0i. So the homogeneous component, like in the FRW metric, this is just 0. But now essentially I want to introduce fluctuations which carry one outside index I. So what I can do, for example, is I can take one spatial derivative of a scalar quantity, where scalar quantity means there's no index, or I can take a vector quantity, right, where vector quantity means that there is an index, and in both cases I have one outside index I to match the outside index I here, and then for convention I add 2 times the scale factor here. And to make sure that this is a pure vector quantity, this Si, I'm going to impose that the del I Si is 0, so that's divergence free, which essentially means I make sure there's no scalar component inside the Si. So I really just have a pure vector component here and a pure vector component here, which comes from the derivative of a scalar. So here we have one scalar, which is B, and one vector, which is Si. Or you could write it as S vector if you prefer. So now we move on to Gij, so the purely spatial component, right? So in FRW metric, this is just a squared 1 times delta Aj, and that will be the end of it. And now essentially we want to add fluctuations, but again, such that in total we have these two outside indices A and J, right? So what we can do is we can add a scalar fluctuation here to the 1. We can also take two derivatives of a scalar quantity, right? That would also give us something which is two outside indices. So take some scalar quantity f, take two derivatives. Or of course, we can take only one derivative, but instead take a vector. So we can also take something like del I fj, right? So a derivative of a vector. And then because I know that this guy is symmetric, I'm going to add symmetrization brackets here and a factor 2 for convention. And then finally, I can also take a single fluctuation, which is two indices by itself, which is a tensor fluctuation. So, and again, I have to ensure that the vectors that I introduce are pure vectors. So del I fi is 0. There's no scalar divergence inside. And also this h here is trace-free and divergence-free. So again, removing all hidden scalars here. So in total here we get two scalars. So this psi and f, one vector, which is fj, and one tensor, which is hij. And so if we take everything together, in total, this tells us that if we want to describe all possible fluctuations at linear order in the metric tensor, we get 4 scalars. We add everything up, right? So these are phi, psi, b, and f. And these scalars are precisely what we will deal with tomorrow, lecture 3. Oops. Then we have two vectors, which are Si and Fi. So note that this f, I mean, I have a scalar quantity called f and a vector quantity called f, right? And I agree this is confusing, but I'm kind of trying to follow the standard notation in the literature. But these two f's have really nothing to do with each other, right? They're really two different things. And the vectors we will ignore for the rest of the lecture. The reason being that kind of in standard cosmological evolution, if you have vector perturbations initially, they just decay over time. So they are mainly not terribly important. And then finally, we have one tensor, which is hij. And this hij is precisely what we call a gravitational wave. So that would be kind of important next week in next week lectures. And also we will have one homework problem dealing with the gravitational waves. Now, I told you that if you're a more mathematically inclined person, you are probably absolutely horrified by this way of doing things, right? Because I'm just kind of trying to write down kind of all possible combination of indices which add up to the right index structure on the left-hand side. And you may worry, or maybe I've forgotten something. Did I really think of every possible combination, and is this like really obeying all the symmetries of the problem, etc. Right? So this is kind of the quick way of doing it, and it works out correctly. And the reason it works out correctly is, of course, because of the underlying symmetries. But if you want to do this in a more rigorous way, essentially what you would want to do. So let me just put this kind of in brackets here. If you want to do it more in a representation theory style, then what you would say is, okay, let's just do, for simplicity, let's just do this guy, right? So just the spatial components. So you would now say that this Gij, right, is a symmetric tensor. So it means that it's 6 degrees of freedom. So if I now kind of do this step 1, right, so I look at SO3 representations. So So I want to look SO3 reps, which add up to something which is 6 degrees of freedom, is going to be a 5-dimensional representation plus a 1-dimensional representation. And if I now kind of do the second step, and I ask, how does the 5-dimensional representation of SO3 look under an SO2? Then essentially I can decompose this 5. I can decompose in the helicity eigenstates, helicity eigenvalues -2, -1, 0, 1, 2, right? So if you count 1, 2, 3, 4, 5. And then in addition, this 1-dimensional representation is just the scalar under SO2. And then again, you can group here together. So you have one scalar here, one scalar here. You have one vector and one tensor. And if you compare this to what we got up here, 2 scalars, 1 vector, 1 tensor, right? So it matches. So 2 scalar, 1 vector, 1 tensor. So if you know about representation theory, this essentially tells you that we found all the relevant contributions up here, right? That things are consistent. If you don't know about representation theory, you can just forget about this last 2 minutes and just do what I did up here, right? And just kind of look for things which have the correct index structure. Right, so now we're nearly at the end, but let me take 1 minute to point out kind of one important fact, and that is gauge invariance, because now we have all the ingredients to understand this. So with gauge invariance, I'm now referring to gauge invariance under coordinate transformations of general relativity. So any physical quantity that you compute should be invariant under x mu goes over in x mu plus epsilon mu, right? The physics should be the same at different points in space. But now this epsilon mu, we can do the exact same decomposition as we did beforehand, right? The scalar component, there's a scalar component and there's a vector component, and the vector component again can be written as either the divergence of a scalar, right, or really a vector, where again we have to ensure that the vector is divergence free. So this epsilon parameter, right, just exactly the same way as we did above, contains 2 scalars and 1 vector. So I don't care so much about the vector, as I explained, but the 2 scalars are important because it means that I have the gauge freedom to remove 2 scalar degrees of freedom, right? So our metric up here had 4 scalar degrees of freedom, but they are not all independent, yeah? Because through gauge transformations, I can remove 2 out of these 4 degrees of freedom. So actually, there's kind of only 2 physical degrees of freedom in here. And this is then something that is important when you continue to compute things. Yeah, you have to make sure that, well, either you carefully pick a gauge and work in that gauge, or you need to make sure that you don't pick a gauge, but that all the quantities that you're working in are gauge independent quantities, right? Because at the end of the day, your physical observable may not depend on your gauge choice. And this is the case for scalars. For tensors, there's not this problem, right? Because here, this epsilon parameter, so the coordinate transformations of general relativity do not contain any tensor degrees of freedom. So tensors are just, they are what they are. But for scalars, we will have to pay attention to this gauge invariance issue. Okay, so let me stop there and take questions. So there's many questions in the chat. Does somebody want to speak up? Maybe summarize what is the, otherwise I start reading the chat from the top, but maybe if somebody. Okay, so let me just start with Draw's question, right? So this is the 415 question. How can the energy of the inflaton field can be thermalized if there are no interactions with the standard model? Very good point, right? So here I'm just essentially gave you a toy model with just a single scalar field phi and no interaction with the standard model. And indeed, this would not suffice to do the job, right? We will need to introduce interactions with the standard model at the end of the day in order to actually connect to observables, absolutely. So to give you an example, one model of inflation is, for example, Axion inflation, right? So like you have an Axion like field, and you can, that kind of determines the type of couplings that you can have. And you could also have gravitational couplings to the standard model fields. But yes, you will have to introduce some couplings. This Fourier decomposition assumes that the universe is spatially flat. Well, I'm doing the Fourier decomposition essentially after I factored out the scale factor already, right? So essentially I'm doing it in co-moving coordinates. So I don't have to worry about the FRW metric. I am, in fact, and I will in most of the lecture kind of assume that this k over a squared term in the first three-band equation is small, right? Because we know that kind of due to inflation, this term becomes small very quickly. And so I don't want to complicate my life too much by worrying about it. Okay, so there's a question about the So2 Helicity Eigenstate. So the way you get the eigenstates is really kind of you take your scalar field, you perform this rotation, and you kind of see what sort of phase factor you get like you get kind of as an eigenvalue of this rotation, and this essentially tells you if it's scalar vector tensor. That's kind of the formal way of doing it. In practice, as I said, you just kind of check if you have spatial indices or not, or how many spatial indices you have. Yeah, I don't have answering Disha's question about how we can see the vectors decay. I mean, I know how to compute it, right? But I don't have an intuitive quick argument. But we will talk later about, in particular for the scalars, we will see how they don't decay, right? So we'll see how the scalar is a very particular property, and also the tensors, in fact, that makes it such that they don't decay even over very, very long time periods. And essentially, this property will not apply for the vectors. And yeah, so we'll do the computation for the scalars, and in principle, you can do the same computation for the vectors, and you will kind of find that they don't have this property. Okay. There's a question about kind of when did the Big Bang happen with respect to inflation? Yeah, so that's interesting because the name, I don't know if you know, but like the name Big Bang was actually coined by the people who thought it was a ridiculous idea. So like before the discovery of the CMB, right? So in the 50s or 60s, there was a debate if the universe was a steady state, meaning kind of it has a fixed size and it's just static and it just is what it is and always was, or if, as we believe now, kind of the universe is expanding, right? And so hence at some point in the past, it was very small. And it was, in fact, the people who defended the steady state idea who kind of pointed out this singularity that we talked about yesterday and said, look, you guys who talk about the expanding universe, didn't you notice, your theory is complete nonsense because kind of you have this singularity in the past, like there was a Big Bang, or how do you imagine, right? So in some sense, the term Big Bang is not a good name at all, right? And it's not surprising because it was coined by the people who opposed it a lot. So I don't even know where really to put the Big Bang in this picture. Like kind of the idea now that we have now is that we have this phase of inflation, and at the end of the phase of inflation, we connect to the hot early universe, and then things like Big Bang nucleosynthesis and CMD decoupling happen. But in some sense, the Big Bang, so this singularity, is pushed to time of minus infinity, right? Because our scale factor now is not a power law as a function of time, but our scale factor is an exponential function of time. So if you ask, where is the scale factor 0? And this is in some sense the definition of the Big Bang, right? The singularity in the scale factor. This doesn't actually happen at all, right? I mean, the exponential function doesn't get 0 unless you send time to infinity. So in some sense, inflation gets rid of the Big Bang, or it pushes the Big Bang to kind of times which are conceptually outside of what we can observe. Yeah, I mean, concerning literature question, I mean, on the notes yesterday, right, which are also online, I gave some literature recommendations. Okay, yeah, okay, which are the most favorable models of inflation? We'll talk about that a bit when we come to potential observables, right? Because now essentially we've just talked about the background dynamics, right, and how we can kind of get enough expansion to explain the background dynamics. But in order to actually match to observations, we need to talk about these fluctuations, and we'll get there in the next lecture actually. So at the end of yesterday, people were brave enough to talk up, right? But now somehow people have forgotten how to speak and are just writing in the chat, and I'm talking all to myself.
Can I ask a question?
Yes, please.
I wrote it before, but I think it got lost in the thread. One idea, I always understood well how inflation ends and the ethos, but are there any speculative theories of how it started, or what actually triggered the Inflaton field to actually kick in and inflation to start?
Yeah, that's an excellent question, right? Because you need to, if I go back to the plot here, you need to somehow start very far away from the true minimum, right? And this is in fact also a problem, at least in some inflation models, and in this, yeah, it is a problem in some inflation models. So one idea is that essentially this happens at very, very early times, right, where you have a huge energy budget. And essentially, you can have displacements of this phi field, which are just kind of quantum jumps. And normally, a quantum jump is tiny. But here, essentially, because you have such a high energy density, you can actually have quite sizable quantum jumps. And so there's some small probability that you can essentially jump all the way to very large values of phi. And all you need, I mean, you don't need to do this everywhere, right? Because if in, say, some places of the universe, you just kind of jump very close to the origin, well, that place is not going to inflate, right? But if some other place, you jump very far, then that place will inflate, right? And it will essentially become to dominate over all the other places. So if you're an observer, you're very likely to find yourself in a spot that did inflate, right? Because they take off much, much more of the phase space. It's not quite as easy as that, because not only kind of do you need to ensure that you're high enough of this potential, you also kind of need to ensure that locally your field is actually homogeneous, right? Because that's the assumption that we made in the beginning. So kind of you have to find, at some point, kind of in all these quantum jumps, you have to find some spot, some spot in the universe where actually the field value is large, or the potential energy is large, over kind of a sufficiently big spot. Let's say like this, right? And if those initial conditions are met, then inflation starts. And if you now want to kind of compute how likely is this, right, or how likely is this to work, or like how likely is it that we find ourselves in a spot in the universe which did inflate, it becomes a very complicated measure problem, because in some sense you can only, I mean, the things that did inflate kind of come to dominate very quickly, but you don't kind of know how big was the entire initial space. And probably as an observer, you cannot live in the spots that didn't inflate. So it's a bit hard to kind of rigorously answer the question, but this is kind of what people a bit have in mind.
And the idea is that this whole thing happened around 10 to the 19 GeV in terms of the energy scale of the universe?
Actually, we don't know. So as we'll see tomorrow, we can essentially put an upper bound on the energy scale of inflation, which is in order of the Hubble parameter, right? Which is essentially what gives the energy density. we know that the Hubble parameter during inflation has to be smaller than about 10 to the 14 or so GeV. But it could even be much smaller. I mean, we know that inflation needs to happen before BBN, right? So that essentially puts the lower bound. So we know we need the temperature at the end of inflation to be above 10 MeV so that inflation works. But between 10 MeV and this 10 to the 14 GeV, essentially everything is open. And in order to answer this question about what is actually the energy scale of inflation, the best way to do that is to detect these tensor perturbations, so detect gravitational waves from inflation, because that would tell us something about the energy scale of inflation. At the moment, we just have an upper and a lower bound, which are very far apart.
Very good, thank you.
Okay, somebody asked, well, what is kind of the fate of this scalar field today? So it depends on what is the scalar field, right? So as I briefly mentioned beforehand, so one possibility is that this scalar field is indeed the standard model Higgs field. So it doesn't work all by itself, right? So you kind of need to add extra stuff. But you can, by adding extra stuff, you can get inflation to work with the standard model Higgs field. And in that case, it would just still be around in that sense. But in most other models, essentially, yes, you kind of assume that this field phi is some additional heavy field, which did its job during inflation, and then after inflation decayed, can have some very heavy mass, right? So for example, in this model here that we discussed here, so from what we discussed here, just the dynamics, the mass can be anything, right? We got no constraint. But what we'll see tomorrow, that when we actually compute the fluctuations and compare this to observations, we will find that the mass here has to be about 10 to the 11 or so GeV, so very heavy. And so this guy would just have decayed at some very early time and completely impossible to produce in a collider. But it really depends on the inflation model. Okay, so Gabriel is asking how much time did the inflationary epoch last? Well, as I said, it has to have lasted at least kind of 60 e-folds, right? Because that's essentially what we need so that the larger scales which we observe, so the CMB scales, had time to get in causal contact. But it could have been even much bigger, right? Because it could be that the region of the universe which is in causal contact could be much, much bigger than the region of the universe that we observe, right? We can make no statements about the region of the universe that we cannot observe, and hence we can only kind of put a lower bound. Right, so there's a question here, when inflation ended, where did the enormous potential energy of the inflaton go to? And yeah, I mean, in fact, the idea is that this is kind of converted, like that you have couplings that lead to the standard model, right? And you do kind of convert this energy density into a hot thermal plasma. And this is then essentially the hot primordial soup of the early universe that then is kind of the initial condition for standard cosmology, right? And you have a hot thermal soup with all the elementary particles. And as that kind of cools down, all the things that we know and love happens, right? So big bang nucleosynthesis happens, the decoupling of the CMB happens, etc. Okay, any more questions? Or maybe it's in case I skipped over some questions in the chat because I partially had the feeling that they were maybe already answered by other people or answered earlier on, but feel free to speak up if something is not clear.
We can also continue during the Q&A session.
Right.
Because these are, I think, interesting questions, but I'm afraid some people might leave or they have to leave and then they miss the answers.
Yeah, I'm happy with, I don't mind having a break before the Q&A session. So. Okay, then see you in essentially 1 hour, right?
Yes. Thanks a lot for the nice lecture, and thanks the participants for the nice questions. See you.